If you've watched the logic gate videos, then you pretty much already know what 1-4 is about. It's an application of the logic we've been talking about. And in this case, well, the example here is the light in the ceiling of a two-door car. If either of the two doors is open, the light is on. So they're both open, or one's open and the other's closed, or they're both closed. When the two doors are closed, the light's off, otherwise the light is on. So, that should pretty much look familiar. If open is true and closed is false, then you've got basically the or statement here, door 1 or door 2. If they're both true, then light is true. If one of them is true, light is still true, right? Door or door. But if both of them are false, the light is false. Okay, so it works out the same way. And this is what the logic gate looks like if you're trying to draw a schematic diagram of this. You've got an input wire here, and an input wire here, and an output wire here, right? And if either of these two is enough to power the light, then this logic gate is going to be OR. Okay, so let's just sort of go down here. And what we wind up doing is saying true is 1 and false is 0, or 1 means you have an electrical input and 0 means you don't. So 1 is on and 0 is off. And so this is what that truth table looks like again.
The only difference here between the two different charts is that for the bottom one, 1 is closed and O is open. So if the doors are closed, the circuit is open and the light is off.
And we go over here, and this is where they actually introduce you to the drawings that you've already seen in the videos. This is the NOT gate, the AND gate, and the OR gate. And these are the output signals. And again, this is something that should be familiar to you. If the input is 1, the output of a NOT gate is 0, right? And if the input is 0, the output of a NOT gate is 1. And if they're both 1, then the output is 1. But if they're not both 1, then the output is not 1. And for OR, only one of them has to have a 1 in it. The first one does, the second one does, the third one does, and the last one doesn't. And so on, off. Or true, 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 false. Okay, so this is what the gates look like and what they do. And so here is an example of what that looks like. And the truth is, we've already done this, right? But we can do it again. Okay. Here's P and Q. So this would be true here, and then false, false, false. Here is not P and Q, right? Because it went through a NOT gate. And so this would be false, true, true, true. And so these are the values that are the output here of these two functions together. Oh, and there you go. It's right there. Okay, and they check it with the same kind of truth table we just did. So it's making sense what we're doing. Here is Morgan's law in the same kind of notation that we were just talking about. Right? These are functionally equivalent because this is the negation of an and statement, and this is the or statement of two things that are negated. Okay, so in other words, if I have P and Q, and I do the and then I do the not, which is what we did a moment ago, or I do this one, right, which is not P or not Q, you wind up with the same values here as we did a moment ago. False, true, true, true. Okay. All of these are pretty straightforward and easy to read. You've watched a video of a much more complicated one already. All of this is thanks to this man, George Boole, and Boolean logic, covering the reading, how long ago were the algebraic properties of and, or, and not first studied? The algebraic properties of these things were first stated and explored by George Boole in 1815 to 1864. His book came out in 1853, so I guess that's the answer to 1A. 1B, how long ago were these properties first applied to electronic networks? Well, I guess first you'd have to discover electricity, so that didn't happen until later. The first applications of Boolean algebra to the analysis of networks were by A. Nakashima in 1937 and Claude Shannon in 1938. So that's the answer to that. Like I said, these are guided reading exercises. They help you figure out what they think are the important situations here, the important parts of it all. Here are the problems. Use the network version below of De Morgan's law. Okay, not P or Q is equivalent to not P and not Q. Write the input-output table for the left side. Write the input-output table for the right side. And why do your answers in parts A and B establish the two networks are functionally equivalent? Well, let's grab a fresh piece of paper here and do what this says. This says we're going to take P, which could be true, true, false, or false. We're going to take Q, which could be true, false, true, false. We're going to take the OR value here, P and Q. The OR, if one of them is true, then the OR statement is true. So this is true, this is true, this is true, and this is false. And then if we take the negation of that, it's P or Q, whoops, P or Q negated. Right? Do that again so it's a little easier to read. Not P or Q. So that would be the exact opposite of these. I do believe this is what we just did a moment ago, but we're doing it again. It's okay. Okay, so that's that. Then if we do this one here, we have P, and we have Q, and P can be true, true, false, false. And Q could be true, false, true, false. The not P and the not Q are just the opposite. So this would be false, false, true, true. This would be false, true, false, true. And if I put them together as an AND function, right here, then that's going to be not P and not Q. Okay, so if they're both false, this is false. If only one of them is true, it's still false. And if both of them are true, it's true. And we have the same outputs here and here. So once again, we've proven that De Morgan's law works. These two are functionally equivalent. All right, so that's number 2. And that tells us A, B, and C. And then write the logical expression that corresponds to the network below. Whoa. All right, we can do this. Okay, and we have 3 here. Okay, so that's important. Right, we have 3 of them here. We have P, we have Q. We're going to need not Q, so let's put that here. And we're going to need R. So P is going to be true, 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 false, 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 false. Q is going to be true, true, false, false, true, true, false, false. Let's just do R here, which is true, false, true, false, true, false, true, false. There are going to be, if there are 3 things and each one can be either true or false, it's going to be 2 times 2 times 2. Each one of these can turn out 2 ways. The fundamental counting principle says we multiply each of those numbers by each other. So 1, 2, 3, 4, 5, 6, 7, 8. So we should have them all. All 3 could be true, 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 false, true, false, true, true, false, 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 true, true. Yeah, that's pretty much covering them all. Let's, because we can, let's do not Q in another color. This is false, false, true, true, false, false, true, true. Write the logical expression that corresponds to the network below. So first thing we want to do is figure out not Q, which we just did, and then put them together with P and not Q in an OR statement. So this is going to be P or not Q. Okay, that's what it's asking for here. Let's move this over a little bit. Okay. P or Q, or not Q. So if P is true, if one of them is true, then the OR statement is true. So here we've got true, 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 true. So that's actually all 4 of those are going to be true. And then here, not Q is false, not Q is false. So these are both false. So this is going to be false and false. And here, we've got true and true. The not Q is true, so it doesn't matter that P is false. This is going to be true and true. And now we're going to take the output of that right here, which is this, and combine it with an AND operation with the values of R. So in order for that to be true, they're both going to have to be true. So R and P or not Q is the expression we're looking for, which is actually what it asked, right? The logical expression that corresponds to the network below. That would be this, right? It's P or not Q, which is this one. This is R, and this is an AND function. So what comes out is that R and P or not Q. So they both have to be true. They're both true here. They're not both true here, right? We're doing these 2 columns. They're both true here. They're not both true here. They're not both true here. They're not both true here. They are both true here, and they're not both true here. Whoa. So there you go. True, false, 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 true, false. And that's not only the answer to number 3, but it's more than the answer to number 3. And that gets us through the covering the reading, right? Covering the reading. So there you go.